I've officially spent an hour of my Saturday talking to myself in the back room of my house while my husband plays video games. This is sad, but we continue on with measures of predictive power. So once you get out a linear regression line, right, that equation, without the scatter plot, you really don't know how good your predictions are, right? If we look at this particular one, we know there's a heck of a lot. One, we only have 10 data values, and there's a heck of a lot of variation away from this line. So we don't know if we're going to do a really good job of predicting or if we're going to do a really crappy job of predicting, right? And we can kind of tell that there's quite a bit going on in this. And so we don't feel that strongly about the actual values that we're getting out versus, I don't know, a previous one. If I was looking at systolic blood pressure versus weight, I'd feel a lot better about how good my predictions were going to be from this line looking at this scatter plot. So that's what 3.4 is getting at, is the idea that just because we have this linear regression equation and we can get predictions, how good are those predictions? How good is that interpretation of slope? Is it really telling us a whole lot, or is there a lot of variation away from that we're not really getting? So there are some ways to look at the predictive power of our line. The first is by actually just looking at a residual plot. So a residual plot, you're going to take every single error and you're going to graph them. So we can actually say, okay, well, we have been usually off plus or minus 5. So that's about how good we think our predictions are. When you're looking at a residual plot, there's basically 4 things you don't want to see in your residual plot. If you see any of them, they're just indications that your model is not very good and maybe you should have been doing something different. So the first is unusually large values. When you plot all your values, you want to make sure that the actual values, right, this is our errors if you kind of look at this plot below. And they're saying that we are off about plus or minus 2. And that really depends, right, on what the actual units of your y. If our y is height and we're off plus or minus 2 inches, that's not a terrible thing, right? If it's weight and we're off plus or minus 2 pounds, that's even better, right? But if this is GPA and we're off plus or minus 2, that is a horrible linear regression line. So that unusually large really depends on the units of y, and you just have to sort of think of it, we were off plus or minus this much for the values we made the line for. This is either good or bad because of that. Curvature, you don't want to see any nonlinear patterns. What's going to happen with this residual plot, and we'll see it on the next page. In fact, I'll just scroll to it. Oh, don't I? What the? There it is. It's far away. On this page, you don't have to flip your notes to it. Just watch for a second. Is that if we look, so if we see like these 2 dots that are right on top of each other, at our residual plot, we can see the same values, right? It almost just takes our plot and it makes this line into the 0 line, because anybody that we perfectly predicted, like these values are really dang close, we're going to see as having no error, right? Their residual is going to be 0. And anybody that was really far away from the line, right, is still going to be really far away in terms of the residuals. So we can see just from this and this idea that we're just taking this line, the linear regression line, and basically flipping it over, is that if we have a curve in our residual plot, that means there has to have been a curve in the original, right? That's the only way this would have happened. So if you did a scatter plot, you already would have seen this. The residual plot is something to do afterwards, just in case, and especially when you have more than one variable, something you can't really visualize in 2 dimensions with a scatter plot, then these residual plots would be a little more useful. But for this, at least, you should have seen it in your scatter plot. Fanning is an uneven variation, so you can see in this particular example, we're doing pretty dang good. Everybody's pretty close to the line, and we're getting more and more spread out as our x's get bigger. So this is what we talk about when we talk about fanning. So if you can imagine, maybe this is some example about, I don't know, hours spent studying in GPA or something, and maybe we know pretty well what's going on for people who are around the low values, but as we get to the high values, you could be studying really effectively or really poorly. ineffectively and feeling confident, who knows? But this is something that could happen. This does not mean your linear model has to get thrown out. It just means that there's probably a better method to have used, something that will account for not only the change in the actual y, but the change in variation away from the trend as things progressed. The last thing to look for, any individual points that might cause a problem. You see somebody who has a very large residual, that could be an issue. We know linear regression is not particularly friendly when it comes to dealing with outliers. So if you see an outlier in your residual plot, that could be an indication that there was an outlier in the original plot, and it could influence your actual outcomes. So what do we want to see? What we want to see is something like this, where everything looks random, pretty evenly spread out in terms of its randomness, and our values for the residuals are small. So this is the one time that we actually want to see like no trend at all, because in theory we're looking at what's left over after we take out the trend. Now, students do not like the residual plots. They want a nice numeric measure. Every time we have to go subjective with plots, they're upset. So we have a nice numeric measure that'll tell us how good our line is, and that's the coefficient of determination. It doesn't tell us as much information as the residual plot. It doesn't let us see there was something nonlinear going on or some sort of change in variation, some fanning, but it does give us a one number to say basically how good is our line. So this coefficient of determination is denoted r squared, and it literally is our correlation coefficient, that little r squared. Now why it's usually written as a capital R and this is written as a lowercase r, I have no idea. Other than, I guess, somebody decided to mess with intro-stat students and do this to you guys. It is always given as a percentage. Some software will give it out as a decimal. I will always give it to you as a percentage because it is the percent of variation explained. But if you went to your calculator, it gives it out as a decimal, and a couple of different stats programs do that as well. I believe R does. So it's given as a percentage. Since it is something squared, it will always be positive. It tells us the percent of variation in one variable that is predictable from another variable. So, what does this mean? I'll give you a very basic, albeit wrong, but very basic sort of description of this. So let's just say I gave a test. And on this test, I had people scoring from a 0 up to 100. So we're going to keep it really basic. Even though R squared does not use range, range is the most basic measure of variation. So right now, our Y values, our test values, and don't write this anywhere on your notes. Maybe I'll just make a new page. Hold on. So let's say we have exam scores, and again, they range from 0 to 100. And this is just to make life easy on me. So we have our range, and our range is from 0 to 100 or 100, right? So 100 is the range of our values. But there's a lot of stuff that could tell us more about your exam score, right? Because right now, if I had to guess what your exam score was, if I had to predict, I would, I would predict probably that your exam score was a 50, right? Something right in the middle. And that's going to be crap because I'm going to be off plus or minus 50 depending on where you are. So if we could use something else, like say exam score versus time studying, and maybe make a scatter plot, and maybe our scatter plot looks like this, right? So not a very strong trend, but we can see the more time you spend studying, the better your score was, right? But the question is, well, how much did our actual scatter plot, how much did this linear regression really help? So that's where you would go to your residual plot and you'd say, okay, residuals. So this is still about time, and this is our residuals, our little e's. And now all of these little dots are just going to translate to the little dots here. So just pretend these are right. And let's say that the actual spread away from this line, let's say it went, our errors were from positive 20 to negative 20. Essentially what we're saying is the range of our errors, positive 20 minus a negative 20, the range of these errors is a 40, right? And we go, okay, well, that's interesting. We just took something that we had a range of 100 on, and we now have a range of 40. So before, it was like a plus or minus 50 if I had to make a prediction, right, around something. And now it's a plus or minus 20 around whatever that prediction is that moves up the line, right? But it's plus or minus 20. That's as far as we go in either direction. So how much did I manage to improve this? Well, I went from plus or minus 50 to plus or minus 20. I went from a range of 100 to a range of 40. So this improvement is 60, right? Plus or minus 30. I managed to get rid of 30 on either side. And so you can kind of think of this out of the original 100. This is a 60% improvement, right? In terms of the whole range being 100, we've now brought that range down to just 40. So we've improved it by 60. So this is a very wrong basic way to think of this percent of variation explained. But if we have this much variation originally in our exam scores, and we bring down our errors to 40%, we explained 60% of what was going on. That's a really basic way of thinking about it. It doesn't actually use range, it uses variance instead. But this sort of gets you the idea. And if you didn't follow that, don't worry about it. I just wanted to throw it out there for those students who really want to understand what's going on with R squared, what the heck this means. So that's where this interpretation comes from. Blank percent of the variability, so that was what we used range of, in our Y, so in that case exam score. So 60% of the variability in exam scores can be explained by the least squares regression, or the regression line, on exam scores, of exam scores on time studying. We basically explained 60% of what was going on. All right, so what do we need to know? Well, we need to know that interpretation. We need to know some calculations for sure. Know that we can go to this R squared by simply finding our correlation coefficient and squaring it, and then turning it into a percentage. And then we can also go backwards. If we have an R squared, we can figure out our correlation by simply taking a square root. And then we have this last piece here, which is also important. The closer our R squared is to 100%, the more we've explained, and therefore the stronger our line was. It also means a little r was closer to 1, therefore a stronger relationship. Moving on to the next page, we do have those guidelines for predictive power. Greater than 80% has excellent predictive power. Moving all the way down to something less than 25% would have very weak predictive power. So again, just like with the correlation coefficient, I don't think you need to memorize these things. Just know closer to 100 is better, gives us better predictions. Closer to 0 is weaker. With that, I'm going to go ahead and stop this video, and I'll do all the exercises in a separate one.